Welcome back. We're going to start this next segment of the lecture by talking in more detail about couplings. As we described earlier, a coupling is a flow of information from one component or state variable of the system to another. By definition, it's one way. However, two state variables can have bidirectional coupling to each other if component 1 influences component 2, but component 2 also influences component 1. So let's make this more concrete with an example. If you think back to the example of pots on the stove. Let me just adjust my pen settings here. We can represent those pots on the stove, or the state variables describing those pots on the stove, as boxes. So one of these boxes might be temperature, and the other state variable that we're going to consider is going to be water vapor. So as you heat water, it leads to the formation of water vapor. Now this is a positive coupling because an increase in temperature leads to an increase in water vapor. And in the convention of system science, we would represent this positive coupling with an arrow. So I'm drawing an arrow here from temperature to water vapor. And so let's just create ourselves a little legend here. So the arrow represents a positive coupling. And this describes a situation where an increase in component 1, here temperature, leads to an increase in component 2. Conversely, with a positive coupling, a decrease in component 1 leads to a decrease in, this is supposed to be a 1, leads to a decrease in component 2. Okay? So the basic idea behind a positive coupling is that the changes are in the exact same direction. Now let's think about the coupling in the other direction. What influence does water vapor have on temperature? And in thinking through this problem, I encourage you to think about what happens when you sweat. When you sweat, water vapor is essentially created from your body, and heat leaves your body in the form of the vaporization of water. And so the creation of water vapor leads to a decrease in your body temperature. So the signs are opposite here. An increase in water vapor leads to a decrease in temperature. This is something we would represent with a negative coupling. And just to make that clear here, I'm going to change the color to blue. And in system science, we typically depict negative couplings as not an arrow, but as a line that terminates in a circle. Okay? So this feature describes a negative coupling where an increase in component 1 leads to a decrease in component 2. And the reverse is also true with a negative coupling. A decrease in component 1 leads to an increase in component 2. Okay? So just to reinforce that, couplings are one way. A positive coupling means that a change in the same sense. An increase leads to an increase. A decrease leads to a decrease. With a negative coupling, hold on, I'm getting a little bit ahead of myself here. So again, we represent this with an arrow. With a negative coupling, we have the opposite sense of change, where an increase in one variable leads to a decrease in the other, or a decrease in the first variable leads to an increase in the other. And we represent this as a line that terminates in a circle. So let's now walk through a concrete example. In the top cartoon, we have two state variables, the temperature of the room and the temperature of Circle Man's body. So here it looks like Circle Man is very hot, so a high room temperature leads to a high body temperature. Both of these state variables are in the same direction, and that an increase in room temperature leads to an increase in body temperature. So this would be a positive coupling, which we would represent with an arrow. And just to make this clear, this is a positive coupling. So let's now consider the reverse. What effect does room temperature have on, or what effect does body temperature have on room temperature? So when Circle Man's body temperature goes up, he's going to turn on the air conditioner to decrease the room temperature. So this, the change is in the opposite direction. An increase in body temperature leads to a decrease in room temperature. And so that would be a negative coupling, which we would depict with a line that terminates in a circle. Here we go. So this is our negative coupling. Okay, that's pretty straightforward. So let's make this a little bit more complex, and talk about feedback loops. So a feedback loop is a self-perpetuating mechanism of change and response to change. So remember, when we define feedback, it's a condition in which one state variable influences the other state variable, but that other state variable also influences the first state variable that changed in the first place. And so this situation of body temperature and room temperature actually does form a feedback. So when someone's body temperature goes up, they're going to decrease the room temperature. So again, we can draw this line terminating in a circle that represents a negative coupling from body temperature to room temperature. But when room temperature goes up, this person's body temperature is also going to go up, and so we have to draw the positive coupling, which we will depict as an arrow. So this is a way to represent a feedback on one of these coupling diagrams. In this particular case, we have what we would refer to as a negative feedback, which is a stabilizing feedback. So let me write some of these definitions down. Feedbacks can be either positive feedbacks or negative feedbacks, where a positive feedback is a runaway or destabilizing feedback. It's a destabilizing process. And a negative feedback is a stabilizing process. And here's a neat trick. If we're looking at a coupling diagram, you could just multiply, you could go around the circle. So we could go from body temperature to room temperature and then back to body temperature, and multiply the sign of the couplings that we encounter as we traverse this circle to determine whether it's a positive feedback or a negative feedback. So if we go around this circle, we have a negative sign, which we could interpret as a -1 times a +1. And the result here, the product, is a -1. And so we know that this bidirectional feedback represents a negative feedback. Okay, so we could summarize this by saying, to determine the nature of the feedback from the coupling diagram, multiply the signs as you go around the feedback loop. So here, I'm just going to use a different color. Let's pick green. So here, the product of that feedback loop equals -1 times +1, which equals -1. So therefore, this is a negative feedback. So this slide just summarized what I just told you. Assign each positive coupling a +1, assign each negative coupling a -1, and then trace your way around the feedback cycle, which in some cases might consist of more than one of these state variables. If the product of all those couplings is +1, it's a positive feedback and it's destabilizing. If it's -1, it's a negative feedback. So in the previous example, we have a negative feedback loop. In other words, the temperature of the room is not going to shoot off to hundreds of degrees or to absolute zero as a result of this thermal regulation. It's going to stay around room temperature, 68 to 72 degrees Fahrenheit. Let's switch this situation up a little bit, though, to look at what would happen or how a positive feedback might develop through this situation of thermal regulation. So we have on the left over here, we have Helen in a room. On our right, we have Phil in a room. And somehow the wires between the thermostat and the air conditioner / heater got crossed. And so let's work out what's going to happen. And now you'll notice we have a more complicated coupling diagram. We actually have 4 state variables. Of interest are Helen's body temperature, Helen's room temperature, Phil's room temperature, and Phil's body temperature. So let's start with Helen's body temperature. And Helen is very cold, so she's going to turn the thermostat up to make the room warmer. But this actually doesn't affect her room, it affects Phil's room. So when Helen's body temperature goes up, or when Helen's body temperature goes down, Phil's room temperature should go up. And so this is a change in the opposite direction, which we should represent with a negative coupling. So let's just go ahead and draw that. So we have a line that terminates in a circle. And we'll give this a -1 for clarity. Now, when Phil's room temperature goes up, his body temperature is also going to go up. We already discussed that situation with Circle Man, and this is clearly a positive coupling, which we'll represent with a red arrow, and we'll also assign a value of +1. Now when Phil's body temperature goes up, he's going to want to turn the thermostat down, but that actually impacts Helen's room temperature. So when Phil's body temperature goes up, Helen's room temperature should go down, and this will be represented as a negative coupling. So we draw this again as a line that terminates in a circle, and we assign that a value of -1. And then when Helen's room temperature goes up, as you might expect, her body temperature would also go up. You know what to do at this point. Give it a positive coupling with a value of +1. So now what's going to happen? So let's trace around this feedback loop. And so to figure out whether this is a positive or a negative feedback, we would take a -1 times a +1 times a -1 times a +1, and that should give us a +1. And so you see this is a positive feedback cycle. So we have -1 times +1 times -1 times +1 equals +1, which is a positive feedback. So as Helen gets cold, her actions are going to impact Phil's room temperature, which is going to cause him to turn down the thermostat, and her room will get even colder. So she'll get colder and colder and colder. whereas fill will get warmer and warmer and warmer. So this is a runaway or destabilizing feedback. We'll go through some more examples in the next segment.